So we're starting the academic year. It's in a different location today because there is a conference about clusters of galaxies in Philips, and we were good citizens and let the conference take over. Our regular place, as you know, is Philips Auditorium. We'll start next week with a routine of this colloquium at 11, and then at 12:30, the ITC lunch. We have new people, and we will talk about them maybe at lunch. Otherwise, you know, it's really exciting to read the archive every day because there are lots of new things happening, and that means that we will have an exciting year because we have something to say about these new things. And I would like to welcome everyone. Those that are new to the ITC, we will have a reception for the new academic year on the 28th, I believe, if I remember correctly. That's a Saturday. And we hope to see all of you there. It doesn't matter whether it rains or shines. We will do it indoors if it rains. So please come to the ITC reception. And without further ado, we'll introduce our first speaker. Please.
Yeah, so we'll start with our own Oliver Zier, who is one of the new people. He's a starting ITC fellow. And Oliver was tightly connected to the extended ITC family throughout his academic career. So he finished his PhD at MPIA in 2023, where he worked with Volker Springel, who is like one of the ITC alumni. For his PhD thesis, Oliver got Otto Hahn Medal from Max Planck Society. And then he moved here to Boston and did 1 year of postdoc at MIT working with Mark Fockelsberger, another alumni of ITC. And now he joined us as an ITC fellow. Oliver is one of the core developers of Gadget 4 and AREPO codes, which some of you might have heard. So if you need an local expertise in either of these codes, you know the person to ask. And please, Oliver, take it away.
Yeah, thank you very much for the introduction. It's really nice to finally start here. I mean, I've been visiting while I was at MIT quite often already, the ITC, but it's nice to be finally officially also part. So yeah, I mean, the topic of my talk today will be also especially about plans, what I want to do during my time at the ITC, which will be like analyzing the early universe by using large-scale simulations. So I show some of my collaborators, which is not only Mark and Volker, the two former ITC fellows, but also Rob O'Connor, Aaron Smith, then Lars, and then Rudiger Parkmore from MPA. And since it's my first talk here at the ITC, I also added some few slides about what I did before I started with this project, just so you know what else I might be interested in. So I mostly work in numerical astrophysics, so I use computer simulations, and my main tool is the AREPO code. So here have just a few slides. I mean, it solves the Euler equations, it can do self-gravity, and a lot of additional physics. So you have galaxy formation, wave transfer, etc. And the special thing about this code is it's using like this unstructured Voronoi mesh shown here. Originally, AREPO was written by Volker Springel, and this mesh itself can move in time. And typically, it moves with the local fluid velocity. So you can see here in the center, you have the fluid moving to the right. The same also with the cells. On top, you move to the left. So the cells move to the left, and you get this nice Kelvin-Helmholtz instability with this unstructured mesh. This has some advantages typically. So you get like a high accuracy. It's quasi-Lagrangian, so because you move with the flow, and especially you get an adaptive resolution. So if you have a higher density, you typically get smaller cells, so you get a higher spatial resolution, which is important for cosmological simulations if you want to have high resolution galaxies and other things. The disadvantage is it's more complicated. On the one hand, of course, well, it takes more time to develop new methods for it, but also it's more expensive because you have to construct this mesh. And originally was inaccurate also in shear flows. So if you want to do disk simulations, especially cold disk simulations, it was quite inaccurate. So this is just a very short summary of what I did in my PhD. I did not cosmological simulations, but instead I did accretion disks with AREPO. And so I show on the top one example of a two-dimensional accretion disk. It's super cold. It's orbiting around the central object. Nothing should actually happen because no additional physics is included. And originally, the left side was, before I started my PhD in AREPO, the code was not able to keep this disk stable. just get numerical noise and instabilities. And after my PhD is the right one, you can actually, for several hundreds of orbits, evolve this very cold disk with high accuracy. Then implement a shearing box approximation in the code, which allows us to study the internal structure of small parts of a disk with very high resolution. And then I study different instabilities with this shearing box in AREPO, gravitational fragmentation, macular rotation instability, Rossby wave instability. I implement non-ideal MHD in AREPO, and I also developed Gadget 4 to get in Fokker. And some project I'm working on now as a side project with students is, for example, the collapse of a photostellar core with non-ideal MHD in AREPO. We check like different magnetic field orientations, different dust sizes, and it's worked on together with Alexander Meyer from MPA and Thorsten Naab. And in the future, we publish now one paper. We do like zoom-in simulations in like a turbulent box, and then see actually if you have a realistic boundary conditions, how does this affect the magnetic field, the formation of stars. And then long term, you like want to extend it, is like solar metallicity, extend to possibly star formation. And then another plan, which is like a more long-term plan we have, is to do like ISM patches in the shearing box, similar to like the Silk project, so that you really have a patch of the ISM with very high resolution, solar mass resolution, and you can test different physics in galaxies. But yeah, that's more like a long-term plan we have. But now I come finally to the start of my real talk, or like what I actually will be my main work here at the ITC. And that's to study the Epoch of Reionization. So here I show on the top a short history of the universe. Well, we have the Big Bang at the beginning. The universe is fully ionized. At redshift 1100, we get recombination. The universe becomes neutral. And then during this time, density perturbations were able to grow. And then around redshift 30, we started to form the first stars. Those stars started then to emit radiation. And we slowly get those small ionized bubbles. Then later, the first galaxies were forming because structure started to grow and grow. You get more and more of those bubbles. And at some point, the bubbles overlap and the full universe was reionized around redshift 5.5 to 6. And then this was around redshift 5.5, around 1 billion years after the Big Bang. And then since then, the galaxies were growing and so on. And so if you want to study this, what people can do is to run large cosmological boxes. So these are some examples done already with the AREPO code, always the ITC quite involved, the IllustrisTNG, and the Millennium TNG project. So you take a box, you add like self-gravity, you start at high redshift, you add self-gravity, you add some galaxy formation model, you assume periodic boundary conditions, and then you let it evolve. All of the simulations were quite successful, but they're also quite expensive. So I show here, that's the number of CPU cores you needed. You can see also it becomes more expensive with time, 8,000 cores, 25,000 cores, and then Millennium TNG was 123,000 cores. And also the runtime becomes more and more expensive. Millennium TNG, when it comes to the number, one simulation was around 170 million CPU hours. An issue with those simulations is that you assume in the IGM a uniform UVB background, which is like spatially homogeneous. It's depending on the redshift. And of course, this might be true or useful for low redshift universe, but at least at a high redshift universe, you have those bubbles, so your radiation field is not homogeneous at all. And so this was the birth or the idea behind the THESAN project. And so the idea is you use like the EllustrisTNG model, which works at low redshift very well, and you add to it radiation transport. So you actually really evolve locally the evolution and the transport of radiation and the ionization of our hydrogen and helium. And well, yes, this then led to the THESAN project. It was like the first papers were published in 2022, also led by Rahul Kannan, Aaron Smith, two ITC fellows at that point, and Enrico Garaldi. And you can see, I think that's probably the neutral hydrogen fraction, or I don't know what actually to show here. You see how you start high redshift and then you get more and more bubbles until your universe is completely ionized lower redshift. And some more technical things about this simulation. Itself, the box was 95 co-moving megaparsec cubed size. It ended at redshift 5.5. At that point, the universe was mostly reionized in the box, except some small part. They used 2,100 cubed cells, so not as small as the number of particles, and then the IllustrisTNG model coupled with a radiation transport. And I can show here small illustration how it looked like. Side redshift 16, the left side shows the neutral hydrogen fraction, on the right side the radiation field, and you can see how like those small ionized bubbles start to grow around individual the first galaxies. So you start slowly build up this inhomogeneous radiation field, and then if you go around redshift 8, those bubbles start to slowly merge, and then at some point the universe is completely ionized. And also you see on the right side, you build up this uniform or almost uniform radiation background. And then well, at redshift 5, you have this very small neutral region left. Yes, I mean, these are just some examples of like different, like the field around different halos or different halo sizes. You can see because we have this radiation transport, you really get like those self-shielded filaments on the right side, while the medium around it, you get fully ionized. Then also since then, quite a lot of science was done. Like you can study, 21 centimeter, you can study the halo mass relations and so on. I think it's quite successful. I think there are published around 15 papers with the simulations already, and then that is still ongoing. But there is one problem, those simulations are very expensive. So already like IllustrisTNG or TNG was very expensive, but if you add radiation transport, it becomes much, much more expensive. The reason is that you have like your time step criteria, so like the integration time steps you can use. And if you add radiation transport, it's given by this. So it's the size of your cell, this like a spatial resolution divided by the speed of light. If you would do like normal IllustrisTNG, it would just be the speed or like the sound speed, or the speed of light is much larger. So you get significantly smaller time steps. So you have to do much more calculations. And even also THESAN only run into redshift 5.5, so only a very short amount. It itself required 28 million CPU hours, 58,000 CPU cores. So quite expensive. And if we look on the right side, I show the total computing time and where the time was actually spent during the simulation. You can see, yeah.
So how exactly are you describing the radiation?
It's like
is it just an energy density, or is there a flux?
No, it needs to be.
Or is it the complete ray distribution?
No. It's like the M1 method.
It's the M1 method. Okay.
And it's for ionizing photons only.
Yes, it's only 3 bands. It's like the hydrogen ionizing really one.
Obviously, there is also X-ray.
Yes, I will come to that later.
Okay.
It's the future.
So I can answer the question. Can you go to the previous slide?
Yeah.
Yeah. In the spectrum, I noticed that you have a bomb at like more than 10 microns. So if you just use like Popstar and others, the first one is really understood going up and down. What really create the other bumps that you're seeing over there?
I have no idea. I just took this, like, I just took it like from the source. I didn't do the THESAN simulation, so.
Right.
Sorry. Yes. Yeah, but I mean, if you look at the runtime, you see like 53% was radiation transport, and then the rest was like domain composition and polarization overhead, 3 gravities like gravitational force, and other modules. And if you look into those 53%, we see 30% of it was MPI communication, like so you have to exchange messages from your parallelization. And so if you want to run like larger boxes, or you want to do like more complicated RT or like any more physics, you really have to optimize the code, because otherwise it's just getting too expensive. And I mean, this is one example if I run a smaller box. So it's the same THESAN model, but just on one node, so 72 cores, 256 cells. And you see again, the radiation transport is 78% in that case, actually. So the RT is just too expensive. And this was then actually the idea for my first postdoc together with Mark. And the goal was to optimize the code, especially the radiation transport, so that you're able to run larger, more expensive simulations and also use larger machines. And so, because I mentioned the word exascale computing, just a short introduction, what does exascale actually mean? Here I show the, on the x-axis is the years, on the y-axis is the performance, and the performance of a computer is measured in the number of operations you can do per second. And now we are actually at exaflop, so that's 10 to the 18 flops per second, the largest machines. And this, yellow brownish line shows you like the fastest computer we have at the moment on the planet. The green line shows you the sum of all the 500 largest, and the blue line shows you the 500th largest machine. And you can see that now with Frontier, we have the first exascale machine. And if you go back, we had just 2008, we had the first petaflop machine. So actually we have a lot of more computing power nowadays, but we have to see how we can use this power efficiently. Typically, those computers consist of thousands of computing nodes connected by a network. You can typically use like sending messages around to do this parallelization. And how does one of those like supercomputers look like? That's one example of a computing node. And you can see that here we have in total 63 or 64 CPU cores. We have additionally 8 GPUs, which most of those supercomputers nowadays, they use GPUs. And actually, if you could read that, 99% of the supercomputing power comes from the GPUs. So if you want to get access to those machines, first of all, you have to support GPUs. Otherwise, you don't get any access anyway. And if you want to make your simulations faster, you should use GPUs also just to make it faster. And another thing is all of those 64 cores share the same memory, so they can read and write to the same physical memory, which you can also use to optimize communication. And so we published this paper, which is now also accepted, where we optimize our code, so port it to the GPUs, and additionally optimize communication. And the first thing what we did was to get down this communication cost, so overhead from parallelization. And so I show here, as a function of here, the number of cores per node, so the number of cores which share the same memory. That was on the Max Planck clusters, and you can see it's going up. So you can exploit this because instead of like sending messages around within your computing node, you can just read the memory. You don't have to really exchange something. And additionally, if you send messages to some other computing node, instead of like everyone is talking to everyone, you can just bundle it and send like less but larger messages, which also helps you to use the network more efficiently. And I just show one example. That's like a scaling test. So it's an H2 region test and a weak scaling. So if we increase the size of the number of nodes we are using, we also increase the computing, the problem size. So we just increase the number of cells. And here, the important part is down here. It's the ratio of the runtime from the old scheme to our new improved scheme. And the green line is only the communication. The black line is for the radiative transfer itself. The left one is on engaging. That's the local MIT cluster we have. And you can see if you go like already to 1,000 cores, we get a speed up of factor 2 for the RT and for the communication even more. The right one is on Raven. It's the Max Planck supercomputer. And I mean, it has a better network and also more optimized, but even there you see we get around 30% speed up. So it depends a bit on the hardware you're using, but in general, it already leads to quite some significant speed up. And then the next thing we were doing is, as I said, like we have to support GPUs. So a short introduction, what actually makes a GPU special compared to a CPU. I show on the left side example. So the CPU, you have like a few cores. They're typically quite smart. They're optimized for serial work, so one work by one. And yes, so that's the example. The GPU instead, you have much more cores, but they are much more stupid. So the two work like in groups, and they have to do like the same work at the same time. But if you have like parallel work, so like you have to do the same calculation 100,000 times, the GPU is optimal for that. And so like a modern GPU can run like more than 10 to the 5 threads in parallel. They can really do like 100,000 operations at the same time. So if you have enough parallel work to use it, the GPU will be much faster. If you cannot parallelize it, the CPU will be faster just because it's doing like serial way. The problem is all the GPUs require special programming. So you cannot just take your CPU code and let it run on this GPU. But instead, for example, for NVIDIA, you have to use CUDA, AMD, then FIP, and you really have to optimize your code for this architecture. And yes, so these are some things. We took the radiative transfer from our repo, ported to the GPU. Things we had to think about. So we rewrote our code into independent loops, which means like loops over interfaces of cells. So if you have to do the same operation per cell, we can do actually every cell like by an independent thread. We also have to optimize the memory layout. So instead of storing like all of the particle data together, you instead store all the properties together in an array. It just makes like memory access faster. We do some algorithmic changes because not all libraries we're using on the CPU exist also on the GPU. And we have to explicitly copy memory between CPU and GPU. The problem is then there are dependencies between tasks. So like one MPI task, if you have like a prioritization, might depend on another task. So what we do is we were splitting all of the work into work which is like can only requires local data. We run this with like a low priority, and then work which requires like communication, and run this with higher priority. And so we get like some, like if the communication is done, in the meantime, the GPU can do local calculations. And then once we get like data from other tasks, we can run those with a higher priority. And so now I come to the result. This is again tests on Raven. So it has 70 on one node only. It has 72 cores. It has 4 A100 NVIDIA GPUs. And on the left side, I show the result for pure photon transport. So like just a double mesh, no hydrodynamics, just photons and let them travel. On the x-axis, I show the number of cells per MPI task. So what we were doing is we just increase the problem size, but always running on one node. And on the y-axis, I show the time we need in seconds per step per cell. And the black line is on, if you run the RT on the CPU, it's a flat line, which makes sense because it's serial work. So if you have like n times more work, you just need n times more time. And the other two lines are on the GPU. So by default, only one MPI task can use the GPU at a time. NVIDIA had this CUDA MPS, multi-process service, which allows that several tasks can use the GPU at the same time. And that's important if like one task doesn't have enough work to really use this GPU, like the full parallel capacity of the GPU. And so we see this in the black and the red line, if we don't use this system. For very small problem size, we actually slow the CPU just because there's not enough parallel work to do. But if we go like to very large problem sizes, like 10 to the 6 cells per task, we see a significant speed up. And this green line, if we activate this process, you start with a much smaller number just because all of the MPI tasks can run at the same time on the GPU. So like you can utilize the parallel performance, parallel capacities better. But then again, if you run like large enough, like if you have enough parallel work, it doesn't really matter too much. And so in the end, on this node, we get like a factor, like a speed of a factor 15. The right side, I show the same plot, but this time for an expanding H2 region test. So we just set up a local source. We have like ionizing radiation. We have like thermochemistry running, and then we get an expanding H2 bubble. And again, we see around a speed up of 15 in this more complicated setup. But of course, for production runs, we don't want to run all H2 regions, but instead we want to run actually cosmological simulations similar to THESAN. And so for this test, I was running on one node a smaller version again of THESAN, 256 cubed. For redshift 49 to redshift 5, the same physics. And additionally, I was using at redshift 5.8, I was taking the THESAN, like the box I got, and then just making periodic copies to create larger boxes. I don't have to run like to do like scaling tests. So I don't have to run the full simulation from redshift 49, but just a very short time. And so on the right side, I show the H1 fractions, so the reionization history, which looks fine. And then this is the result for the large simulation on one node from redshift 49 to redshift 5. The left was again the CPU run I showed actually before. 78% was RT, 120 node hours. If you run it on the GPU, we actually go down to 32 node hours. So it's a factor 4 faster. And additionally, RT is only 17% left. And then the rest, like gravity, mesh construction, which is actually ideal because now we're not bound anymore by radiative transfer. But instead, well, if we want to make the code faster, we have to optimize the rest of the code, which we're actually also working on for AREPO-2. And then I show scaling tests. The important thing is, again, down there, that's the runtime for the CPU divided by the GPU, so the speed up we can get. The left side is a weak scaling test, so we increase the number of cores, but also we increase the box size, so the number of cells is constant per core. The black line is the full simulation. The green line is only for the radiative transfer. And you can see once we use like more than one node, we get a speed of around factor 13 consistently, even like in this more complicated setup. And the full simulation time is around factor 3 to 4 faster. It goes a bit down just like if you use, I think these were 2,004, 5,000 cores. The reason is just because the RT itself, the fraction of the RT in total runtime goes down. So if you optimize that, the relative speed up is smaller. On the right side, I show the results of strong scaling. So we take a fixed box, increase the number of cores, And then we can see that actually the speed up goes down if we use more cores. And it's again a problem just because there's not enough parallel work to do for the GPUs. And then, well, the speed up goes down. But the important thing is whenever we do any THESAN simulations, we always on the left side with the number of cells per core. So actually we expect even there like a speed up of 13, at least on this architecture typically. Okay, yeah, now that we have like this new,
Sorry to interrupt. Can I just ask a question about your pie chart from 2 slides ago?
yes,
So are each of those constrained by the same thing in the GPU? For example, is it all memory bandwidth? Is it total memory, or are they each high arithmetic intensity?
you mean on the right side?
On the right side, yeah.
Yeah, so only the RT runs on the GPU, the rest runs on the CPU.
Yeah, right. But I'm asking on the GPU, are you constrained by total VRAM or memory bandwidth or what?
It's depends a bit. Like some parts are mostly because we do like all the calculations in double precision. And so like thermochemistry is mostly just by calculations, throughput limited. Some other stuff is more by our memory accesses because we use still the unstructured mesh. So our memory accesses are not that ideal for the GPU sometimes. And that limits us. I mean, it's also the issue that because we use like not the same time step for each cell, but instead we have like a hierarchy of time steps. They're like those very small degradation steps, only a small part of our particles are active, and they're not very easily parallelizable. Yeah, I mean, I think there's still ways to make it faster than 17%. Like, I mean, there's still some. I mean, actually, we are participating like in a hackathon from NVIDIA and NASA at the moment. We try to get it further down, but yeah, I think there's probably some low-hanging fruits, probably more low-hanging fruits than like in the CPU part, which is optimized over years.
It doesn't really, if you just compare those numbers like for like rest ones, like 3% of 120 is almost similar to 10% of 32, right? So are you saying that like different individuals may not be really speed up? Like,
oh, I mean, those things are actually the same between those two.
oh, okay, great.
Like those are still running on the CPU, so there should be no change in the runtime. The only thing which changed was the RT implementation. So like 20% of 32 should probably be 5% of 120. Yes, so the first application, which is actually not using the GPU optimization, but only like it's optimized parallelization, is the THESAN-ZOOM project, which I will talk further. Well, it's below there actually to my lunch talk later. And so these are like zoom-in simulations into the original THESAN simulation box. So in total, there were 14 galaxies selected from a THESAN volume. We simulated high resolution, and they use like a SMUGGLE model. So they actually use a real multi-phase ISM model for additional physics. So they have like more radiation bands. We will have like molecular hydrogen. It has dust physics in it, and up to I think 100 solar mass resolution. The halo mass, those 14 galaxies have different halo masses from 10 to the 8 to 10 to the 13 to really check different halo masses, and it runs until redshift 3, so even a bit further than the Epoch of Reionization. The special thing about this is that we can use the large-scale radiation field from the THESAN simulation for the zoom-in as a boundary condition, so we really have like a self-consistent setup. I mean, the project that's led by Rahul Kannan, that former ITC fellow, and then Eva Pupla, Aaron Smith, Josh Borrow, Enrique Aldi, Laura Mark, me, and more people. But yeah, I mean, all the simulations are finished. We are analyzing them at the moment. Hopefully in November you will find them on archive. But yeah, during the lunch talk, I will get you some more information about POP3 stuff formation in those simulations at late redshift. The second project is the THESAN-VARIANT project. So the idea is we take again the THESAN box, but we don't zoom in individual halos, but we zoom in into smaller subboxes. So like subbox of 10 megaparsec cube size. And then we choose those 9 regions by choosing like a lower than average density, average cosmic density, higher density regions. And then within those density regions, we choose like early, average, and late reionization history. We still use like this large scale radiation field from THESAN, but because we only simulate like a high resolution, like a smaller box, we can have like higher resolution, but it goes like 8 times higher resolution, and we can run it to lower redshift. So like ES redshift 2. And those simulations, because they're not that expensive, like they only require maybe a few computing nodes, but it just takes a long, long time to run, like 80 days, for example. And because we use the GPU, we can get a run factor 4 faster at the moment. Instead of like waiting 80 days for the simulation to finish, we can run it in 20 days. Yes, the setup, I mean, I'm personally leading the project. The first simulations are running. We got like some small allocation in Texas for the first tests. And if it's working, we can hopefully get more time to run larger simulations, or more higher resolution simulations. And then the other main project I'm leading is the THESAN-XL project. So the idea is we want to run larger THESAN boxes, significantly larger THESAN boxes. So the goal is to run, instead of like this almost 100 megaparsec cube, run 400 megaparsec cube boxes. Because it's so big, we have to use a bit lower resolution, 8 times worse mass resolution. In addition, I have X-ray bins in the simulation. And we want to run, like, because 64 times 8, it will be 4,200 cubed cells. So it's around the size of Millennium TNG. And we plan to do like 3 runs at this resolution. And yes, the goal is like, because we have like this higher box, I mean, here's an illustration. That was the original THESAN box. This will be like our final goal in the simulation. So you see, well, it's much, much larger also. And it allows us to trace like better the distribution of neutral hydrogen, which is important for 21 centimeter cosmology. Because we have like this larger box, we get much better statistics to compare with JWST. We can also have the formation of more massive clusters or like groups. We can study the effect of quasars on reionization. And also, if we want to do like ray tracing through our box, we can use longer light cones just because we have a larger box. We don't have to use too much periodicity. And it's more like a side advantages. At the moment in AREPO is in the community. We don't really have experience on running on large GPU clusters. But if we want to continue using those big machines, we have to do that in the future. So we'll also be able to get experience how those big machines actually behave in production. Do we have to do any code changes or what can go wrong? I mean, for THESAN-XL, we plan to use around 10,000 GPUs in parallel. I was able to run it for the proposal. I was running for a short time this, but yeah, there's a lot of additional things which can go wrong, which you might not expect if you run smaller simulations. We submitted a proposal to run on Frontier, this exascale machine I mentioned before. And ideally, if we get the time, I think we're in November, we would like to start with that in 1st of January, the simulations, and then hopefully end of next year to have the first results. And then I come to the summary of my talk. In general, radiative transfer is very expensive. We optimize it by using like a shared memory and deploy it to GPUs. We got like a speed up of like about 13 to 15 to the former CPU implementation, which then also on the one hand is important because we need less runtime, but it's also important to get access to really the large exascale machines because they require GPU support. And then 3 projects I'm working on. For THESAN-ZOOM, I'm just analyzing some data. So we have like a multi-phase ISM at higher redshift. So it's there's zoom-in simulations. So that's perfect if you want to really check how does the ISM behave, how does the GGM behave with a lot of physics. The THESAN-VARIANT project, where we want to run like a THESAN similar box, like a sub boxes to lower redshift, and have a higher resolution than THESAN, and THESAN-XL to do like large scale reionization. And yeah, my office is B219. I still have my MIT email there, but I hope I will get a CFA email soon. Still available there. And yeah, interest like here. If you ever want to come by to an office to talk about anything, like I know numerics, reionization, ISM, star formation, anything interesting. I don't know, or you have some cool hikes here in the White Mountains you can recommend. I'm just open to that. Yeah, thanks a lot.
All right, questions?
Yeah, I guess you focused on the computational aspects and the challenges, but of course the physics is still perhaps even more challenging. And so maybe you can comment on that. First, the before redshift 8 recombinations matter. The recombination time, even in the uniform intergalactic medium, is less than the Hubble time. After redshift 8, it's the other way. So recombinations are less important in the smooth intergalactic. So do you take care of that? And the other question is, now with the Webb telescope, there are galaxies that were not expected. And obviously reionization will depend on how you model them. And so would you like to comment about redshift larger than 10? Because there are lots of discussions in the literature recently.
Yes, so I think the problem about redshift, like if you want to run like those THESAN-XL project, I'm not sure if you really are able to say too much about those very massive, very high redshift objects, just because we still use like the Spring-Hörnquist model like to model galaxy formation. And I'm not sure if that's like because we cannot have like those feedback-free star formation. Those things cannot work in the model.
You don't have population 3 stars.
Exactly.
Yeah.
So I think like for this is probably more for the late time reionization. I think for those probably you would need like something like SMUGGLE, like so there's THESAN-ZOOM project where you really have like a multi-phase ISM structure. I think simulation like that would be more suited for that.
Okay, and recombinations, do you take that?
Yes, I mean
You have recombinations in your code? Okay, so ionized bubbles can recombine and disappear.
Yes, I mean if you run out of like if you run out of photons, like we have full non-equilibrium chemistry network running there. I mean for the computing part, like so the problem was that we could not do more complicated physics just because we are bound by the computing power. So there's things like use like reduced speed of light, approximation, those things which are not perfect, but we have the constraints because we just cannot do better because we just don't have the time. And so that's was the idea that we do like better codes or like faster codes so we can actually do like more physics.
So earlier you said that it's all M1 based.
Yeah.
Which is a kind of a low order moment method. But then you're also talking about light cones extending across the box. I'm getting a little bit confused on exactly how is the radiative transfer being done?
I don't know, the light code is more like in post-processing.
It's in the post-processing.
Yeah, we don't do any light.
Oh, okay. So the post-processing, you're using long characteristics or whatever and using the big light cones, but the simulation is just moment-based.
Yes.
And there is an evolution equation for the radiation field.
Exactly. Yeah, we just have moment-based, so we have like a photon density and a photon flux in each cell, and then we just evolve.
And then the interaction with the gas in each cell.
That's then run like separately, like in a non-equilibrium chemistry network. So the photons get absorbed and
that is some implicit method you need to take care of it, or?
Yes, so on the CPU, we use like an implicit method. The problem is this library we use does not exist on the GPU, so we use a semi-implicit method and just subcycle fast enough.
Oh, okay.
That's a good thing about a GPU because we can do like the 100,000 cells in parallel, so that's fast enough. Problem in a CPU would be slower. But there we just say like, oh, if we change like the thermal energy by more than 5%, we do like smaller steps.
And that never kills you? Because I can imagine occasionally the interaction is so strong that you need really tiny time steps.
No, it has not killed
It does
us.
not bother you, okay.
Not so far. I mean, because we can really do like a lot.
You can do it a lot, okay.
Yeah, I mean, but for these things, it's really, this was all maybe like computationally really optimize the code for like the memory. Actually, we only use local memory. We really check like, oh, do we need like single, double precision, those things, because that's where the speed up is.
Great.
Yeah.
Have you thought about using the so-called Grace Hopper superchip, which is NVIDIA's CPU GPU hybrid? It's very expensive, so whether or not it's worth it would depend on the answer to my previous question, but it's like a terabyte per second of GPU memory bandwidth.
Yes, well, I mean, we at the moment we just use what we can get by applying for computing time. We don't have our own. Yes, but I mean, I think like the new exascale computer in Europe, like Jupiter, I think it's based on that. Like they have like NVIDIA CPU and NVIDIA GPUs combined.
Yeah.
I'm not sure about the architecture. Like, I'm not exactly sure about the architecture there, but I mean, the code should run on those machines too. And well, if you get time on Frontier, there are more ideas about more simulations. So we probably also try to get their time.
Actually, I have a follow up to this. So why did you pick CUDA for this as opposed to some like more generic framework? Because I guess like now it's like more a gamble. It's not clear which frameworks will stick. So what was the motivation for CUDA?
All because it's like in some way the simplest thing. Like otherwise we didn't really know which framework we should choose. Because I mean, some frameworks come up, then they might disappear again, and you depend on like, I mean, CUDA will always exist as long as NVIDIA exists and NVIDIA exists.
Okay.
So what is the alternative to CUDA?
There was like AMZ, But there are also frameworks that allow you to like you develop your code for a specific framework that then can cast to like on a compiler on a compilation time to like different frameworks like CUDA or like NVIDIA specific, AMD specific, whatever.
OpenCL, but
Yeah, like this or others.
I mean, there's like Crocos, or like I
Oh,
think
yeah,
it's
Crocos,
quite used
yeah,
like
Crocos.
Athena, and so you write like your code in this framework, and then you say like, oh, and compile for NVIDIA, compile for AMD, and yes, but I mean, for us it was like we just didn't know what to choose, and so I think CUDA is quite nice to start because it's quite clear. I mean, the point is we use very simple GPU, like we don't really use like the newest hot things in NVIDIA and CUDA. So it was quite simple to also port it to AMD. Like AMD has like HIP, it's like their CUDA version of, I don't know, should not say that, 60, but it's like, well, it's not a copy, but it's very simple.
And according to the stock market, NVIDIA is not going anywhere.
Yes.
So it's okay, safe to stick to them.
Yeah, but actually it's very like, so we ported it to HIP. So actually on Frontier, we're running it on AMD GPUs also. So they call it, I mean, it's just a header file where you say like define CUDA malloc as HIP malloc. It's like 10 lines of, well, 15 lines of code. But yeah, it's running on AMD and NVIDIA GPUs. It doesn't run on Intel GPUs because they have their own framework, but I don't know how well it will go.
Any other questions? Points for discussion? I had another question about the results that you showed comparison of different simulation. Like I think you showed THESAN, Croc, other I think it was like ALMA's functions. You said that they're like, yeah, this. I was thinking about the top left plot, like storm scale, which is like I guess like one of the basic
Yeah.
you want to get from the and simulations seem to be like all over the place there. So I was wondering what's your take on this and
Well, so I haven't written the paper, so you know, but I assume they always claim that THESAN is doing very well compared to what we expect. I mean, the problem is a lot of those early universe galaxy formation models are not really tested also at lower redshift. So like they somehow try to get like higher redshift properties correct. The idea is, or the claim also with THESAN as well, we use IllustrisTNG, so we know the model works for low redshift, it's like some way self-consistent. If that's true, is of course another question, because if you had RT, maybe your thing will still change, but it's also a claim in THESAN at least.
but this is do you see that? Do you see like that if you include RT, so you have like feedback from explicit radiation transfer on galaxy formation or
So I think the galaxies at like redshift 5.5 look quite similar to IllustrisTNG galaxies. Because I mean, but yeah, we don't know, of course, what happens at lower redshift. Probably it should work because, you know, then once you have like this uniform UV background and you have like radiation transport, it gives you a uniform UV background.
Right.
Not much should change anymore, but you know, we have never done it, so we cannot claim it's
right?
really,
But what like so what redshift is this? Like it's just one. Yeah, I guess it's a high redshift.
probably. I mean, it's why I'm also surprised why the other ones are so not right. Yeah.
All right.
And this is maybe just following on Avi's question. I mean, I guess I am nervous about, you know, there are lots of luminous galaxies out of redshift 10 or 12 or 14, and when I looked at some of these outputs, you know, it seems like the simulations are not always able to predict the number density that we're seeing, and so do we actually really have a discontinuity or an inconsistency between the models that are perhaps successfully matching the observations at redshift 4 to 8 and what's needed to get things going at redshift 10 to 14. I'm not sure what the answer is, but it just seems like the luminosity function evolves more slowly than the halo mass function does, for example. So I do worry that we're missing a key piece of this.
Yeah, so it's probably true. I mean, as I said before, I don't think like Spring is very useful. Like it's able to do that because you somehow have like this assumption you're like in an equilibrium state of star formation. This is probably not true at very high redshift that you have like I mean, that's probably true for lower redshift, but once like you talk about very old objects, it's probably not true. So I guess in that case, you might really have to really explicitly evolve like a multi-phase ISM model and really see, can you get like those, I mean, like those feedback-free star formation and those things, like to get really high stellar masses. Because I mean, I think just spring conquest will just give you like an average smooth thing, but probably those things are not average smooth, but like bursty probably, I guess.
Another way to put it, which I guess needs to be mentioned these days, is that natural intelligence is also important, not just artificial intelligence or computer. I mean, making the computer grind faster is not necessarily the best way to make progress. We should also think about the underlying physics. It's
So
not
old-fashioned.
I'm so old-fashioned, yeah. I'm still advocating for thinking, not just.
No, I'm not saying I'm not thinking, but it's, I guess it's more that, I mean, I'm not actually sure there's that much time that's elapsed. So it's like, I'm not sure that it's safe to say, oh, redshift 12 is just different than redshift 8. It's only like 100, 200 million years difference. And so.
But the metallicity was lower. That's one difference.
Well, not in the galaxies we're seeing.
Oh,
I mean, you know, they're not necessarily that low. There's dust, so I don't know. It's not primordial. I don't think we should just say these redshift 12 objects are like all POP3. They're not.
What do you think they are? Why are they different?
Well, I don't know, but I'm saying, I guess my point is the number of halos at a given mass, you know, changes by a factor of 10 from redshift 12 to redshift 10. And we don't see the number of galaxies. So like it's not obvious why a galaxy in a given 10 to the 10 solar mass halo would behave particularly differently at redshift 12 to 10. There might be some slow changes, but it's not obvious that it's vastly different. And yet there's a factor of 10 more in the N-body catalogs. But there's not a factor of 10 more in the galaxy catalogs. It's not, I mean, there's more, but it's not a factor of 10. So it's somehow things really do evolve in light to mass ratio, light to halo mass ratio. Things are evolving relatively slowly. And I feel like it would be important in these simulations to try to dig into that, because I'm nervous that bubble sizes and other things are going to be hard to trust if we don't understand the behavior of the extreme objects at redshift 10 or 12.
Could it be cosmic variance affecting your observations?
Absolutely. Well, I mean, yes, there's clearly large scale structure. Like you don't get the same thing in every set line. This is very true.
But
and so when you find one or two objects, you should, you know, your error bar on the luminosity function from that may be a factor of 10. Like there could be lots of variance. So I definitely agree it's early days on that side of things. But it's not that there's only one object out of redshift 13 and above, like we have found several, 5, 6, something like that. So they're not 0, and they're not small.
You could probably say something about this from THESAN-ZOOM runs, right? Because we have a bunch of like small galaxies.
Yeah, so I think for that point it's better suited to really analyze that. I mean, the problem is we still have in THESAN-ZOOM, we don't have a POP3, like a real POP3 model, so.
But at least you can see like how the explicit ISM, how the like switching to explicit ISM.
Yes, I mean those things will be interesting. And also you can get like an escape fractions out of those things.
Yeah,
self-consistent.
So the other difference at high redshift is galaxies are denser because the universe is denser, and that could account for a given halo mass for a different.
I agree with all those things. I'm just, it's not that it's a factor of 10 in density. It's not a factor of 10 in time. We're talking about, you know, we're only talking about delta, you know, deltas, you know, change in redshift from 12 to 9. It's not
You see a step function kind of change observation.
I'm not saying it's a step. I'm saying that the halo mass function is increasing very, very quickly. The luminosity function is not changing at all.
Okay, if there are,
Go ahead.
no, I was about to say if there are no any quick comments, questions, we can end here. And thank Oliver again.